Today what we're going to be looking at is going to kind of try to follow the order of the book. So, last time we talked about these antiderivatives, your rates of change and things like that. We're going to start talking about something that initially might seem a little bit unrelated, but it's not really unrelated. And what we're going to be looking at is finding certain areas and then finding certain total changes. So, this is really pretty closely related to some stuff that we talked about at the end of the previous lecture. So the first thing that I want to consider, and this is going to be a somewhat straightforward sort of thing to consider. It's not really straightforward, but it's going to be a bit of a simpler case than what we're going to say in a moment. Let's suppose that we have f of x is bigger than or equal to 0 on some interval from a to b. And we want to think about what is the area of the region under y equals f of x above the x-axis from x equals a to x equals b. So this is one of those things that's a little simpler to think about maybe if we have a picture. So let me draw a picture for you. Here's maybe my x-axis, my y-axis, here's my a, and here is my b, and then maybe I've got some function that looks like this going from a to b. So we are interested in the area of this region here that I've shaded in. How could we find that area? And how could we even define the area? Well, let's start off by thinking about the case where f of x is equal to a constant. If f of x is just equal to k, this is a rectangle. So the area should be equal to k times b minus a. Right? That's what we get from rectangles. We know that this is what they should be. There's not really anything tricky going on here. Now, the next case that we could think about is, what if f of x is piecewise constant? So what do I mean by piecewise constant here? I mean, what if this is a piecewise defined function and on each interval where it has a different definition, it's just equal to a different constant. So essentially what we're saying in this case is we split up the x-axis between a and b. Let's suppose that we split it up into, let's say, c1, c2, up to ck, and then we have b, and we have f of x is equal to k0 when a is less than or equal to x less than c1, and then it's equal to k1 from c1 up to c2, and so on. So on each piece, it is a constant. Well, then on each piece, this region is just a rectangle, right? So the overall shape that we're going to get, if it is a piecewise constant, is something like this. And excuse my tiny little picture. So let me just make a picture with like 3 pieces on here, or 4 pieces total actually. Maybe we have something that looks like this, okay? But on each one of these pieces, we've just got a rectangle, right? So each one of these forms a rectangle. The total area then is going to be k0 times c1 minus a plus k1 times c2 minus c1 plus k2 times c3 minus c2 plus all the way out until we get out to kn. I don't know why I put a k there. Let's put an n. Kn going from B times B minus Cn. Okay, so we just add up the areas of all these rectangles. So in this case, the answer is fairly simple. Now, what if we don't have any sort of piecewise constancy? What if we just have a general f of x bigger than or equal to 0 on A to B? Well, the answer to this question goes back all the way, really. I'm sorry, this thing is having horrible issues with glare. The answer to this question kind of goes back thousands and thousands of years, at least to the ancient Greeks. And I'm sure other people, other mathematicians were working this stuff out as well. But as you know, our mathematics, a lot of the stuff came down to us from the ancient Greeks more or less directly, at least, those of us in Europe and America. And so we tend to look at what the ancient Greeks did, but other people probably did this kind of thing as well. It's not something that I would expect only to be discovered once. And the idea that the Greeks had was something they called the method of exhaustion. Now, this method of exhaustion that they had was not exactly what we do today, but it was sort of the fundamental idea was there. It's just the details that we switch around. And we switch around the details because, well, the way that we do it today just makes everything more uniform. The Greeks they had this idea of the method of exhaustion, but they would use it sort of in kind of different ways in different circumstances. So nowadays, the way that we define it, everything is very standardized. There's just one way that we do everything. The Greeks kind of were like, okay, we've got this method, and let's just try to apply the method in various situations. So here's an example of the method of exhaustion that they used. One of the things that they did was they tried to think about the area of a circle. Well, how would you find the area of a circle? The answer that they came up with was very clever. What they said was, let's break up the circle into polygons with a finite number of edges. And then you can break up the polygon into a bunch of triangles. Now, if you make it a regular polygon, then actually all of these triangles are going to have the same area. So they break up the polygon, they make a polygon inside the circle. And then what they noticed is that if you calculate the area of the polygon, you'll get something that's reasonably close to the circle, at least if you have a large number of triangles in here. But you are going to be missing these little pieces on the edge. However, as the number of vertices in the polygon goes up, what's going to happen is that these little slivers that we're missing are going to get smaller and smaller. And so the Greeks observed that essentially what they were doing was taking a limit as the number of vertices in their polygon goes to infinity. That's what they were trying to do. So the method of exhaustion is really trying to take an infinite limit. It's just sort of, they didn't have the concept of a limit explicitly, but it was basically trying to find a limit like this. And you may be interested in seeing that Archimedes was able to use a similar technique to actually find the area under a polygon. So if you look up Archimedes and the method of exhaustion, you'll see how he was able to do that. He took the area under a polygon. I do not remember the details, but he drew like a triangle like this, and then he drew more triangles into the remaining spaces, and he was able to come up with the actual area under a, did I keep saying polygon? I meant parabola. He found the area under a parabola by using this method of exhaustion. And he did it by filling the thing up with triangles. I don't remember exactly how he did it. Now, the problem is that all of this stuff that the Greeks were doing, like I said, they didn't really have, they had two problems, actually. Well, three problems. Problem one, they didn't actually have the limit defined. So this method of exhaustion was more like an intuitive heuristic method, as we might call it, than an actual precisely defined thing that mathematically definitively makes sense. So that's our first problem. Now, our second problem is that, well, they didn't know how to compute limits. So in most cases, they weren't able to actually find a specific answer for the method of exhaustion. Our third problem is that they just kind of used the method of exhaustion however it seemed like it might possibly work in the problem at hand. They didn't have a systematic approach for defining what should the area be in general. They just kind of winged it. And in a specific situation, they might be able to come up with a solution. Like Archimedes was able to solve the problem for the parabola, but his method wouldn't necessarily work for any other function because he doesn't know how to compute the limits and things. So he just kind of got lucky that he was able to come up with a specific approach that happened to work. Well, he didn't get lucky. I mean, he was smart. He thought about the technique and he came up with a method that works in this one instance. It doesn't necessarily work in other cases. So what we want to do is we want to sort of take this idea that the Greeks had. We want to take this this method of exhaustion, and we want to make it precise using the notion of a limit, and then we want to be able to use our notions of limits to talk about what these things actually come out to be. So here is the way that we are going to estimate the areas. We're going to estimate the areas using rectangles. So the idea is that if I have some A and some B here, and I've got some function, I can break up this region into rectangles of width b minus a over n, where n is the number of rectangles that I choose. I'm sorry, let's see if I can fix this horrible glare situation that we've got. So the width of them is going to be b minus a over n, and we sometimes abbreviate this as delta x. And then what I need to do is I need to pick the height of my rectangles. Well, for the height, I'm going to choose them to be f of what I'm going to call xi star, where xi star is some point along the ith base. So in other words, x1 star is going to come in anywhere in here. It can sit anywhere along this interval. x2 star is going to be any point in this second interval. x3 star is any point in the third interval, and x4 star is any point in the fourth interval. Hopefully you get the picture, okay? It keeps on going with this pattern. Now, that means, of course, that there's a lot of choices involved, because I could take my xi star such that the rectangle is kind of small, or maybe I can take it so that it's bigger. Like this first rectangle, we have lots of choices for the height. And for the second rectangle as well, we've got lots of choices for the height, right? I could even choose something where it's in the middle here, where I do the evaluation. So different choices of xi star are going to give me different possible choices or different possible heights for my rectangle. And then what I'm going to do is I'm going to add them all up. Now, the way that we write such an addition is using summation notation. So this is a Greek capital letter sigma, and then we write I equals 1 up to n, and then we write f of xi star times delta x, which is the area of each one of these rectangles. So what this means is it means f of x1 star times delta x plus f of x2 star times delta x plus all the way out until we get to f of xn star times delta x. Now, like I said, there's a lot of choices involved here. Because we get to choose the number of rectangles, and we also get to choose the xi stars. Now, here is what we are going to say. Something like this is known as a Riemann sum, after the mathematician Riemann, who he came up with a lot of really cool stuff. But one of the things that he did was he put this sort of thing on a logically rigorous footing. So before him, people had talked about these areas, and we will see why they were able to do so. There's some very interesting properties of these areas that you kind of don't need this definition to see that they have to be true for any reasonable definition of an area. But whether or not such a reasonable definition existed was not so clear, and Riemann was able to show that it did. Now, brief historical interlude, he also did it in a sense, not in the optimal way. Okay, so what we are studying in this class is going to be the stuff that Riemann did. The reason we're doing that is because in a lot of ways, Riemann's method is the simplest. But unfortunately, because it's simplest, it also has some shortcomings, which for our purposes, they won't really matter, but for some technical purposes, they do matter. So later on, some other people, a French mathematician named Lebesgue and somebody else with the name of Daniel, they came along and they came up with other methods for making these notions rigorous that are better from a technical perspective. But they are also much more complicated from a technical perspective. So for that reason, we are not going to be studying their approaches in this class. We're going to stick with Riemann's approach because even though it's got some minor technical problems, it's not so much that it has problems, it just has limitations that Lebesgue's approach and Daniel's approach don't have. However, these limitations don't really matter for us, and it turns out that getting rid of those limitations requires a massive technical pain, so we're going to skip over it. We're just going to do Riemann's approach. So the next thing we are going to do is we are going to define the area under y equals f of x from a to b as the limit as n approaches infinity of these Riemann sums, I equals 1 up to n, f xi star times b minus a over n. And we can only do this if these exist and are the same independent of the choices involved. So remember, there's many choices involved here, and we define the area to be equal to this limit if the limit doesn't depend on the choices. Now, first of all, I got to tell you what the limit means in this context, because we haven't actually defined a limit here. So essentially, what we're going to say, the limit is really the same as the limit for functions. Just think of these as functions of a discrete variable instead of a continuous variable, but we are still just doing the limit as n approaches infinity. So the limit as n approaches infinity of some f of n is equal to L if and only if for any epsilon bigger than 0, there is a capital N, and when little n is bigger than or equal to capital N, absolute value of f of x, or I'm sorry, f of little n minus L is less than epsilon. So it's the same definition as a limit at infinity. It's just the variable is now a discrete variable instead of a continuous variable. Not really that big a deal. So that's what this limit means. But we also need to make sure that this limit exists independently of the choices involved. Now, the good news is that it will exist independently of the choices involved in many cases. And so this is our definition of the area. But before we look at some examples, I want to go on to another sort of abstract discussion here where we're going to talk about generalizing this formula a little bit. So what if f is not always bigger than or equal to 0? So what if there are places where it's negative? Well, we could still define these Riemann sums. We could still think about the sum from I equals 1 up to n, f xi star delta x. But the problem is that when we do this, first of all, I have to make a picture. When we do this, the rectangles that are underneath the axis are going to contribute the negative of their areas. We subtract these rectangles here because f is negative there. Now that might seem like a little bit of a weird thing, because what we're getting in the limit is really the area between y equals 0 and y equals f of x above the axis minus the area below y equals 0 and above y equals f of x. That's what this Riemann sum is estimating. And the limit would really give us this sort of thing. So that's a bit of a weird thing. So for instance, if we look at the limit of these Riemann sums, if I have something that looks like this, maybe I've got this shape here. Well, I can think of this region as having area A1, this region as A2, and this region over here is A3, and the limit of the Riemann sums is going to converge to what geometrically I would interpret as negative A1 plus A2 minus A3. And more generally, I could put these regions anywhere I wanted to. So the ones above the axis contribute their area, the ones below the axis subtract their area. Now that might seem like a really weird quantity to be interested in, but it's actually a really useful one. It's really something that naturally crops up. So this is really actually natural to do, even though it seems weird when you first think about it. Now it seems weird because why would we care about like the difference between the areas above minus below? That's a weird thing. From a geometry perspective, yes, it's a bit of an oddity to be interested in this sort of thing. But here is why it is natural and why the Riemann sum is of interest even for functions that are not necessarily bigger than or equal to 0. The reason it is of interest is, let's think about v of t, where v is a velocity. Now, more generally, you could think of any rate of change that you want to here. But I'm going to do velocities just so we have something specific in mind. If you really prefer something else, you can kind of think of everything I say in terms of some other rate of change. But the nice thing about velocities is, even if you're not into physics, the rate of change of position is something that's kind of nice to visualize, I think. So maybe it's just because I also was in physics, but I think most people, it's kind of a nice intuitive thing to visualize. Other types of rate of change are maybe a little bit more complicated. Now, if I were to consider, here's t, here's v. If we have some time interval and v is constant on the interval a to b, then the total change in position is going to be given by taking whatever v is equal to, let's say it's equal to k, it's going to be k times b minus a. So that is our total change here. If it is piecewise constant, oh, and the thing to notice here is that this is true even if k is negative. See, if k is negative, that just means, remember, velocity is not just speed, it's also direction. A positive velocity means our position is increasing. A negative velocity means it is decreasing. So this is true even if k is negative. If k is negative, it just means the total change in position is a negative number. But that makes perfect sense because positions, the position along some axis can change from a bigger number to a smaller number. That is a negative change in position. Now, if the velocity is piecewise constant, well, we still get that the total change is going to be the sum of these rectangles, but in this case, the total change is going to be, I'm sorry, this is now t and v, not x and y. It's going to be like the area that is above the t-axis. So if we call this, say, A1, and then maybe down here we have this region which has area A2, and then we have this region which has area A3. The total change is going to be the area A1 minus the area A2 minus the area A3. But this is going to continue to be true then, even if it's not piecewise constant. So in the limit, as v of t is no longer constant, and I will say what I mean by that in just a moment. This should still be true. So what do I mean the limit as v of t is no longer constant? Well, here's the thing. For nice functions, you can approximate the function with a piecewise constant function. Like, think about just some arbitrary curve, right? I can sort of approximate that by piecewise constant functions. And what we mean by approximating it is I can make a new function which is always as close as you want to as the original function, but it's piecewise constant. So in some sense, we can talk about certain functions as the limit of piecewise constant functions. Okay, so the upshot of all this is that the total change, if our function represents a rate of change, then the total change is the area below the curve and above the horizontal axis minus the area below the horizontal axis and above the curve. What this means is that the total change is going to be the limit as n goes to infinity of the sum from I equals 1 up to n of v evaluated at ti star times delta t. It's the limit of the Riemann sums. And this is true for any function f that represents a rate of change. It's not something special to the velocity function. It's really just something we would expect for any rate of change. The upshot of this is that we are actually interested in the limit of Riemann sums, even when our function is not necessarily going to be bigger than or equal to 0. If it's bigger than or equal to 0, then we have this nice geometric interpretation that the limit of the Riemann sums is actually just this area under the curve and above the horizontal axis. So that's the nice thing when the function is bigger than or equal to 0. But whether the function is bigger than or equal to 0 or not, the Riemann sums are still of interest because they give us an approximation to the this total change. If our function represents a rate of change, this gives us an approximation to the total change. Now, we're going to look into this in more detail shortly, but I want to just kind of point something out to you intuitively. Because remember, the total change is also the position evaluated at time B minus the position evaluated at time A with dx by dt equal to v. So, this is where we're kind of going to end up with this. The limit of these Riemann sums should actually just be the difference of an antiderivative of whatever function we are talking about. Remember, we were talking about antiderivatives, and we said, okay, so this means the position is an antiderivative of velocity. Well, the total change should just be the difference in positions. That's like literally what the change in position is. But we also just argued that the total change should be the limit of these Riemann sums of velocity. So the limit of the Riemann sums for velocity ought to come out to be the difference in the positions, which is actually just the difference in antiderivatives. And this is where antiderivatives are going to play a role. Because it turns out, if we can prove that the Riemann sums all converge to a single number, so if we can prove that this is a well-defined quantity, then under some fairly nice conditions, fairly reasonable conditions that are often met, then the result, the limit of the Riemann sums, is going to have to be given by just calculating a difference of antiderivatives. And that is what is known as the fundamental theorem of calculus. But I wanted to point it out here this way because I wanted to tell, like, the fundamental theorem of calculus can seem like this very technical, surprising thing. And I wanted to kind of explain, or I hope I've explained it in a way that when we get to it, you will see that it's actually exactly what you would expect. It's not something surprising. It's really intuitively almost obvious. And the reason it's intuitively almost obvious comes from this argument, right? From the fact that the total change should be the limit of these Riemann sums, but also the total change should be given by this sort of thing. So when we state the fundamental theorem of calculus, it pretty much says the total change is given by the areas below the rate of change and above the horizontal axis minus the areas below the axis and above the rate of change, but it's also given by just this difference. And so when we write down the fundamental theorem of calculus explicitly, everything will make a lot more sense here. But before we do that, we're going to want to say a few more things about these Riemann sums. And I think this has gone on long enough, so we'll deal with that in the next lecture here.